Okay, we're going to take a look at experiment 10. And experiment 10 is Ohm's law. We know that Ohm's law says that the voltage is proportional to the current times the resistance. So in this particular lab, we are going to graph voltage as a function of current, and the slope of the graph that we get should be equal to the resistance. So Ohm's law for an object with constant resistance, looking at, again, at the voltage as a function of current, we can see here that we would get a nice straight line if R represented the slope. So again, think about this. V equals IR. If you remember, your linear equation is Y equals mx plus b. Here, there is no y-intercept. The y-intercept is 0, so b is 0. So it just becomes y is now the voltage, x is the current, and m being the slope becomes r. V equals IR, or if you want to write it, V equals R times I, Y equals M times X. So we say that an ohmic device is an object circuit element that has constant resistance. So again, if I vary the voltage, I expect the current to be proportional to that and get this nice linear relationship. However, if the resistance changes as a function of the current or changes as a function of the voltage, then I expect that the slope is not going to be constant because the resistance is not going to be constant. So we're going to look at two different types of objects in this lab today. We're going to look at resistors, and resistors have a constant resistance. And we're going to look at light bulbs, which are basically incandescent lights, where we send electricity through a tungsten filament. The tungsten filament heats up. And for any metal, as we increase the temperature, the resistance should increase. So as the filament gets hot, we expect that the resistance will go up and the slope will become greater when graphing when graphing voltage is a function of current. Okay, so what does a resistor look like? This is actually a smaller resistor right here. And we can see that it has a few different color bands on it. And these color bands are there for the purpose of telling you how much resistance there is. The first band is considered to be the first digit. The second band is the second digit. The third band is what is called a multiplier, or the power of 10. And the last band represents tolerance. In this particular case, we have a resistor with I know it looks a little brown. This is a red, black, green, silver color code. And if we translate the colors into digits, red is 2, black is 0, green is 5, but that's the multiplier. So we have 20 times 10 to the 5. And then the last band is what we call the tolerance. That tells us how well the manufacturer guarantees the resistance to be that value. Here it's silver, so they guarantee it to be plus or minus 10%. Let's do this again with another resistor. Here we have a green, blue, orange, and gold. And green is 5, blue is 6, orange is 3. So this is 56 times 10 to the 3, okay? Or 56 kilo ohms plus or minus 5%. All right. Now we are going to do this experiment with two resistors. One's going to be a 10 ohm resistor. The other one's going to be a 100 ohm resistor. And basically, we have a computer interface which is going to send a ramping voltage up and down. We'll call this a triangular wave, or they're oftentimes called triangular waves, where they go up and down. And if you graph them on an oscilloscope, they would look like, a sawtooth pattern. And that's what you see right here. We are going to have this pattern go up and down at a rate of 60 hertz. So every 60 seconds, it'll go up and down, then back up. The amplitude will be 3 volts, so it'll go from -3 volts to +3 volts. And as I said, the frequency is going to be 60 hertz. Okay, so we're going to connect a 10 ohm resistor, first of all, to the computer interface, which is going to ramp up and down the voltage while measuring the current. And then the computer is going to graph the voltage as a function of current, where again, the slope is going to be equal to the resistance. So this is what it looks like schematically set up. You can see we put one of these resistors in the springs right here. Again, it's black, black, brown. I'm sorry, brown, black, black. I'm reading it backwards. Brown is 1, black is 0. So it's 1, 0 times 10 to the 0 plus or minus 5%. So that's 10 ohms plus or minus 5%. So it's probably good from 9.5 ohms all the way up to 10.5 ohms, as long as we're within that. So again, we run the experiment. Here's actually what it looks like. You can see the resistor sitting in there. And again, brown, black, black, okay? Here it is in the little spring holders. Those are going to electrically connect the computer interface to the resistor. And what we also see is we see 2 little connectors that go to the interface. This is actually just a circuit connector. And once we've done that, we can just run the whole program, and the program will basically, the program will basically graph. Here we have the output. We have voltage in the Y direction. We have current in the X direction. And if this is done properly, it will go right through the origin. Now, we've had a little bit of a problem with some of these systems. And unfortunately, there's a little bit of a voltage offset or a little bit of a current offset. So if we look at what we have shown here, and this is very important, so take note, okay? It says, use a scope's built-in analysis tool to determine the voltage for the 10 ohm resistor. Click Smart Tool, move the Smart Tool over the coordinate points. Instead, what we're going to have you do, instead of looking at individual points like you see right here, okay? Hold on one second. Like you see right here, here they're using the coordinate tool. You're simply going to run the slope tool and use the slope to get the proper value. So again, look where it says here, use the coordinates of the points to determine the ratio of voltage versus current recorded in lab notebook. The X coordinate is the current, the Y coordinate is the voltage. Again, the computer is going to do it for you. You are going to basically say that the slope is equal to R for these cases. All right, so slope is going to be equal to R, and we'll just worry about calculating the resistance from that. All right, so I've actually taken the data, and this is important because this is the actual data that you're going to use for the 10 ohm resistor, and this is what it looks like. And as you can see, I've used the slope tool. Oops, this jumped to the next page. I've used the slope tool, and what we see is the slope, and then it gives you some uncertainty. So there is slope. M is equal to 10.1, so that's 10.1 ohms. If you do a little calculation in your head, you see that that's 1% higher than the rated value, but that's well within the 5% tolerance, okay? Remember, the manufacturer guaranteed that the resistance was 10 ohms plus or minus 5%. Plus or minus 5% puts you in a range from 9.5 to 10.5. So this is perfectly fine. Okay. All right. let me just clear that out, and there's our first result. So that's our first data. Again, don't worry about finding a point on the line and determining the slope from that. Because we have a little bit of an offset problem with this, I'm having you just rely on the slope. So what do we know from this result right here? Well, slope's constant. I get a line. So that tells us that the resistance of the resistor is constant, okay? Also, it validates Ohm's law. Notice that here, if the resistance represents the slope of the graph, when I graph I want to say velocity, when I graph voltage versus current, okay, then obviously if this resistance is 10 ohms and I get a slope near 10, I get a straight line. Basically, I am showing that Ohm's law is valid for this case. Okay, so there's my 10 ohm resistor. Not surprisingly, I get a 10 ohm slope. And now I'm going to replace it with a 100 ohm resistor. And of course, you'll see that our 100 ohm resistor has, this is actually backwards in terms of where everything is. So you do a little check mark here. It has a brown, black, brown stripe. Brown is 1, black is 0. So 1, 0 times 10 to the 1, 10 times 10 to the 1, or 10 times 10 is 100. So that's a 100 ohm resistor. Last, I have the gold band. So this is 100 ohms plus or minus 5%. 100 ohms plus or minus 5% tells me it's good from 95 ohms up to about 105 ohms. Okay, so again, I'm going to run the whole thing through. Okay, I'm going to run my experiment, and I'm going to see what I get for a graph. And this is the actual data that I got. And well, we're a little bit close to the lower end of the tolerance, but we didn't go over it. It's a 100 ohm resistor. When I did the slope, I got 95.6 ohms, okay? And, once again, success. Straight line. The voltage is always proportional to the current. If the slope is equal to the resistance, this shows that Ohm's law is valid, that voltage is proportional to the resistance times the current. So those are my two resistors. And again, resistors are used because they have a reliable, constant resistance. Now I'm going to take a look at a light bulb where we don't have a constant resistance. Remember, I'm only going to get a straight line here if my resistance remains constant. So my next setup, I'm going to actually slow things down a little bit. Now, originally, the way that this was set up is I had, let's go back to the original thing right here. Just annotate this and notice a few things here. First of all, the amplitude was 3 volts. I'm going to drop that down to 2.5 volts. The frequency at which it would ramp up and ramp down is 60 hertz. That's too fast for the light bulb to respond. The light bulb takes some time to heat up and cool off. So I'm going to have to slow that way down. And because I'm going to slow down the rate at which the function repeats itself, I'm also going to make my sample rate lower. So this is what I had set up for the resistors. Now notice that I'm going to use very different readings or very different settings for the light bulb. Okay, so here we go. All right, so here's the new values that I have. And we can see that, first of all, we've dropped the voltage down a little bit. We don't want to send too much voltage through the light bulbs because we can burn out the filament. And most importantly, we've dropped from 60 hertz down to 0.3 hertz. In fact, when I ran this, I actually dropped it down to Even lower than that, I dropped it down to 0.1 hertz. And also I can drop my sampling rate down because my function is not going up and down as much. Okay, so what does it look like? Well, for different frequencies, I will get a different amount of hysteresis. I slowed mine down so much that I really didn't have much hysteresis at all. But again, I hooked the light bulb up with these jumper wires and ran the experiment so the light would slowly increase and then slowly decrease. And I got something that looks like this. Now, let me just explain what you're seeing right here. First of all, you're seeing one of the problems that we have with the setup. We're seeing an offset in terms of the voltage and the current. My axis should really look something like this, okay? So when we're doing this, you're asked to actually calculate the voltages up here. You're actually asked to calculate the voltage and current at a few different places on this and use that to talk about the resistance. You're not doing this for this, okay? Instead of taking discrete points, you're going to just look at this qualitatively and say, well, what's going on at different points on this graph? Okay, down here, my slope is really, really low. Okay, that's indicative of a low resistance. That's when the light bulb is cool. There's not enough current going through it to light it up. But as the current gets greater and greater, the filament gets hotter and hotter, and notice that the slope gets steeper and steeper. So what we know here is when it's hot, we have a high resistance. Okay? When it's cold, there's a low resistance. And going back to the original equation that we had for resistance as a function of temperature, the resistance would increase as a function of the change in temperature. So clearly, for some objects, we don't have a constant resistance. For the light bulb, we would not expect a constant resistance because that filament's getting hot. Okay? So again, this is what I expect. Again, the only difference here is you can see that clearly there is a mistake. The origin's down here, and that's not where the voltage is 0 and the current is 0. For some reason, there's an offset, and the origin should be more up here. Yeah, that's why we're not going to do those extra steps. So let me just get rid of my annotation tool so I can go on to the next page. Questions? Let's go through, let's actually step back. Once again, here are the instructions, and we're going to just modify them a little bit. Start measuring the data, observe the scope display versus light bulb, wait a few seconds and stop measuring. Use the built-in analysis tool of the display to find the coordinates of several points on the trace of the voltage versus current. Calculate the ratio of voltage versus current at each point. Record the form of the curve in your lab notebook. Okay, so you're not going to do this. Your analysis of the data is to simply remark about how the slope of the graph became higher as the current through the light bulb became larger. And again, why does this happen? It happens because the filament is getting hot, and any metal that gets hot has an increase in resistance. Okay, so again, in terms of the quantitative measurements for this lab, going back previously, the actual data, the quantitative data that you record, obviously you're going to include the graphs also, but the slope for your 10 ohm resistor, the slope for your 100 ohm resistor, okay? Those are the only two real quantitative values you have. because you're going to qualitatively talk about how the slope changes for this graph right here. Okay? All right, let's go to the questions. Compare the ratio of voltage and current from the scope display to the resistance of the resistors used. Well, that makes sense. You're going to look at the given resistance, 10 ohms and 100 ohms, and compare them. Probably you want to do a percent difference. Compare them to the actual slope of the graphs. Okay? Now, here, doing a percent difference, you can do percent error or percent difference. Either one is absolutely fine. Should be within the tolerance of the resistor. And that's important because it just says that the manufacturer indeed gave you the correct values. Okay, so the slope of the first graph and the slope of the second graph should match the resistor codes, the color codes that were on the resistors. Does each resistor you used have a constant resistance? Well, the answer to that should be fairly obvious. Look at your graphs. If the slope is constant, then the resistance is constant. Now, the answer to the next question, does the light bulb filament have a constant resistance? Well, that should be obvious. The slope changes, so obviously the resistance changes, okay? The slope of the light bulb is not symmetric. Why is the trace on the scope different when the filament is heating up compared to when it's cooling down? Well, that's because as it's heating up, okay, the temperature is increasing, but as it's cooling down, the temperature is actually less than it was when it was ramping up. I'm sorry, other way around. It takes time to cool down, so that creates the hysteresis. It's not so much symmetric in that there's a hysteresis to it. Okay? I'm going to pause here and we are going to look at this with the streaming camera. Okay, so we're going to do our first resistor. Here it is right there. Okay. I don't know if you can really see that. It has a brown, black stripe, and then a gold stripe on it too. You know, it's a little hard to see, but it is there. So I'm going to place this right in the spring holder and put that right there. And now I'm going to go to the computer and I am going to change the signal generator, right? I don't know how well we can see that. Hopefully you can still trying to get good audio at the same time. All right, so I'm going to change the frequency to 60 hertz and amplitude I'm going to have, I'll keep that at 2.5 volts. That's fine. And our sample will go up to 5 kilohertz. Okay, so we're all set. We're ready to go. Very simple experiment to run. What I can do is I can lower this a little bit. I'm going to lower the camera and I'm going to put it on the screen. Hopefully, because we're having a little bit of an exposure problem right here. It's a little too bright. And hopefully we'll be able to see it pretty well. Turn it this way. All right, I think we can see the screen pretty well. Hopefully this is going to work the way it's supposed to. I'm going to start this and you're going to see it record, okay? And see, it doesn't take very long to get a nice little straight line there. Oh, but this is perfect. This actually came out to a perfect resistance. Now, there's no offset on this one. This one was pretty good. So I'm actually going to save this one. I'm actually going to take my little iPhone. I'm going to do a little record. Okay. So we have a record of that. And go on to the next one. All right, so we did the 10 ohm one. Now I am going to put this is our 100 ohm one. Can't really see it. It's brown, black, brown. So 1, 0, 10 to the 1 with also a gold last color stripe on it. All right, so I'm going to get rid of this one. Get rid of this run. And what's going to happen here is it's going to be a higher resistance. I should see a bigger slope, so I'm going to have to stretch out the current graph when I do this. So again, I'm going to do another run. Okay, notice how this looks. All right, let me go ahead and stop it. And actually here we see some of the problems that we have with the equipment. It's a little bit offset, if you will. See how it's not quite going through the origin like it should? So that's fine. We're going to stretch this out this way. Stretch this out this way. And notice on this particular run, the slope was not quite on the resistance. The slope was 95.3. Remember, it's guaranteed. It's a gold last band, which means plus or minus 5%. So the manufacturer said it's good from 95 ohms to up to 105 ohms. So that's fine. I record that run and go on to the light bulb. Okay, so we got to make some modifications on this one. And we are going to try to get both the equipment and the computer monitor into the same field of view. I'm going to remove my resistor, so that's gone. I'm going to take one jumper wire, and I'm going to send that to the first connector to the light bulb. Here's the second wire. Okay, and that'll go to the other one. So now I've simply just replaced my resistor with a light bulb. And I use these jumper wires basically to get the connection. You know, if you take a look here, this black wire goes to the computer interface. So this little jumper wire just brings it over to the bulb. This brings this over to the interface. And again, the jumper takes it to the light bulb. All right. So let's take our previous result. We are going to erase that. I'm going to try to center this a little bit too. Okay. And I've got to make some modifications. My signal generator, the way it's set up, I can't use it that way. So I'm going to change this to 0.1 hertz. That means that every 10 seconds, it's going to go through one cycle. And I'm going to reduce the sample rate, the rate at which it takes data, bring that down to 40 hertz. It says 50 hertz in the lab. 40 hertz is where I am right there. So let's go ahead and run this. Now, watch this light bulb as I run the whole thing. Hopefully, we're going to get a good result here. All right, see, it's ramping up. Getting bright, and then getting dim. Getting bright, and then getting dim. Okay? Now, what I need to do is I'm going to stop this. Let me get some more data points. Let it go through one more time. This takes a little longer to get than the other case. I'm going to go ahead and stop this. I'm going to remove the slope tool because the slope tool doesn't make any sense here. You know, the slope keeps changing, so to have a slope that really doesn't make any sense. Now again, that point right here, that should be at the center of the origin. It's not, it's offset. There's a little bit of a voltage offset there. So again, the procedure for taking different, individual points doesn't make sense. Record my data. Okay, and look at this. We're going to put the camera on this data, and I can't really zoom. Let me move the chair out of the way just to show you what's going on right here. High quality video productions, right? I'm a college professor, not a, I'm sorry, I'm a physics professor, not a cinema professor. In any case, look at what's going on here. Let me see something that I can use to point it. Again, that's where everything is zero. So what's going to happen here is it's cold, cold, cold. It heats up. It jumps up as the filament gets warm. And as we come down, it's cooling off. So that's why you see that hysteresis effect. The hysteresis is due to the fact that the filament is going to be warming up on the way up and cooling off on the way down. So temperature is actually going to lag behind the current. So we're going to get that hysteresis where the up does not match the down. Okay, but clearly we can see here that the slope gets larger and larger at higher currents and lower at lower currents. Okay, again, look at the slope. Don't worry about the XY on this particular case. All right. So that's about it for the experiment. And, again, I can show you the data as it's going up and down. Let me back off a little bit. Actually, let me rotate this so the light is just within your view. And we're going to run this one more time. This run I'm not going to save. We're going to run this one more time. And we are going to even slow down the cycle here. We're going to go to 0.5. And again, you're going to be able to see how the resistance changes as a function of current. So I'm going to let this go. All right, so it's lit up right now. I'm going to let it cool off. It goes through the origin, then it goes back up, then it goes back down. There's that hysteresis that I talked about before. So watch the orange, okay? It's bright, now it's cooling down, follows that path right there. Now it heats up, see how it jumps? As enough current gets through the filament to heat it up. Then on the way down, there's the cooling part, okay? So the heating part on the way up, where the current's going on the way up, is that little hitch right there, where there's a very rapid slope, okay? And then goes on the way down again. Okay, that'll do it. Stop that. And we can stop the video.